The universe has a way of keeping secrets in plain sight. For billions of years, hidden among the most ancient star clusters in our galaxy, certain stars have been defying the fundamental laws of stellar evolution. They shine with the brilliant blue-white glow of youth burning hot and bright in neighborhoods where every resident should have long ago settled into quiet old age. These stars should not exist. Their very presence represents an impossibility, a cosmic riddle that has haunted astronomers since the middle of the 20th century. Yet there they are, scattered throughout globular clusters like eternal youngsters at a retirement community, their blue light a beacon of mystery against the dim orange glow of their elderly companions. Imagine standing beneath a night sky so clear that the Milky Way spreads overhead like a river of light. Among the countless points of illumination, certain concentrations of stars appear as fuzzy patches to the naked eye. Through a telescope, these patches resolve into spectacular spherical collections of hundreds of thousands of stars, all bound together by gravity in formations called globular clusters. These clusters are among the oldest structures in our galaxy, fossil records of the universe's youth, containing stars that formed more than 12 billion years ago when the cosmos itself was still in its infancy. Every star in such a cluster was born at roughly the same time, from the same cloud of primordial gas, making these clusters invaluable laboratories for understanding how stars age and evolve. Stars, like all living things, follow predictable life cycles. They are born from collapsing clouds of gas and dust. They mature through billions of years of steady nuclear fusion, and eventually they die, either fading away as cooling embers or exploding in spectacular supernovae. The mass of a star determines its fate with remarkable precision. Massive stars burn hot and bright, racing through their fuel supplies in mere millions of years before dying young in violent explosions. Smaller stars, conservative with their nuclear fuel, can burn steadily for tens of billions of years. This relationship between mass, temperature, color, and age allows astronomers to read the life story of a star cluster like pages in a cosmic biography. When astronomers examine globular clusters, they expect to find stars arranged in a predictable pattern. The most massive stars, on which would have burned brilliant blue in the cluster's youth, should have long since exhausted their fuel and died, leaving behind only the smaller, cooler, redder stars that husband their nuclear resources over cosmic timescales. In a 12-billion-year-old globular cluster, the remaining stars should glow with the warm orange and red hues of elderly suns, each one slowly converting hydrogen to helium in its core, methodically working through the fuel that will sustain it for billions of years to come. The hottest, bluest stars should be nothing but memories, their fuel spent eons ago. Yet, when astronomers turned their telescopes toward these ancient clusters, they discovered something impossible. Mixed among the orange and red stars were brilliant blue stars, shining with all the intensity and heat of youth. These stars appeared to be massive, hot, and young, as though they had formed recently, even though their host clusters had not produced new stars in billions of years. The discovery violated everything scientists understood about stellar evolution. In a population where all stars were born simultaneously from the same material, there should be no blue stars remaining. These anomalies seem to have somehow reversed the aging process, regaining the vigor of youth while their siblings marched steadily toward old age. The astronomical community gave these puzzling objects a fitting name: blue stragglers. The term captured both their appearance and their paradoxical nature. They were blue, indicating high temperature and apparent youth, and they were stragglers, lagging behind on the evolutionary path that their siblings had followed. They had somehow remained behind in a stage of life that should have ended billions of years ago. The name also conveyed the frustration astronomers felt when confronting these stellar outlaws. Blue stragglers did not fit into any existing theoretical framework. They were cosmic anomalies, existing in defiance of our understanding of how the universe works. The presence of blue stragglers forced astronomers to confront an unsettling possibility. Perhaps stars could somehow regain their youth. Perhaps, under certain circumstances, an old star could acquire new fuel, restart its nuclear engines, and burn bright again. The implications were profound. If stars could rejuvenate themselves, then astronomers could no longer use stellar populations to reliably determine the ages of clusters and galaxies. And the cosmic clock that scientists had spent decades calibrating might be fundamentally unreliable. Entire theories about galaxy formation and evolution might need to be reconsidered. For decades, blue stragglers remained enigmatic. Astronomers could observe them, count them, measure their light, but could not explain them. Theories proliferated, each attempting to account for how a star in an ancient cluster could appear young. Perhaps these stars had somehow hoarded extra fuel, burning more slowly than their siblings, and only now entering their bright blue phase. Perhaps they had captured additional mass from the interstellar medium, bulking up and reigniting. Perhaps they were not old at all, but rather young imposters, formed recently through some unknown process. Each theory had its advocates and its problems, and none could fully explain the observations. The mystery deepened as technology improved, and astronomers could study blue stragglers in greater detail. High-resolution observations revealed that these stars were not randomly distributed throughout globular clusters, but tended to concentrate toward the cluster centers, where stars are packed more densely together. This spatial distribution hinted at an important clue. Whatever process created blue stragglers seemed to require proximity to other stars. The crowded cores of globular clusters, where stars jostle for space like commuters in a packed subway car, appeared to be stellar nurseries for blue stragglers. Something about the dense, stellar environment was key to understanding these mysterious objects. Spectroscopic studies added another piece to the puzzle. When astronomers split the light from blue stragglers into its component wavelengths, they found chemical signatures that told a complex story. These stars did not have the pristine composition of newly formed stars. Instead, their atmospheres contained heavier elements, the products of nuclear fusion that suggested these stars had lived for billions of years, despite their youthful appearance. The chemical evidence indicated that blue stragglers were indeed ancient stars, not recent arrivals. They had somehow acquired a disguise of youth while retaining the chemical fingerprints of age. The blue straggler phenomenon also appeared beyond globular clusters. Astronomers found similar objects in open star clusters, smaller and younger collections of stars scattered throughout the galactic disk. Even in these environments, certain stars appeared bluer and more massive than they should be given the age of their cluster. The universality of blue stragglers suggested that whatever mechanism created them was not unique to ancient globular clusters, but rather a fundamental process that could occur wherever stars gathered in sufficient numbers. As the 20th century gave way to the 21st, astronomers had accumulated a wealth of data about blue stragglers, but remained fundamentally uncertain about their origin. The leading theories converged on a shocking possibility. These stars might not be rejuvenating themselves in isolation, but rather stealing youth from their neighbors. In the dense cores of star clusters, where stars orbit in close proximity, interactions between stars might allow one star to strip material from another, adding fresh hydrogen fuel to its tanks and extending its life. The process would be a form of stellar cannibalism, one star feeding on another to maintain its youth. This vampire hypothesis explained many observations. It accounted for the concentration of blue stragglers in cluster cores, where stellar encounters would be most frequent. It explained the chemical composition, since the cannibal star would retain its original ancient elements while adding fresh hydrogen from its victim. It even explained why blue stragglers appeared somewhat more massive than typical cluster stars, as they would have gained mass through their predatory feeding. Yet, despite its explanatory power, the vampire theory remained unproven. Astronomers needed direct evidence of the feeding process, observations that could catch stellar vampires in the act. The challenge was formidable. If blue stragglers truly fed on companion stars, astronomers would need to observe binary star systems where mass was actively transferring from one star to another. They would need to peer through the glare of starlight to see the subtle signatures of gas flowing between stellar surfaces. They would need telescopes with unprecedented sensitivity and resolution, capable of distinguishing individual stars in the crowded cores of distant globular clusters. For decades, such observations remained beyond the reach of available technology. Astronomers could theorize about stellar vampirism, but they could not witness it directly. Then, on Christmas Day in the year 2021, humanity's most powerful observatory launched into space. The James Webb Space Telescope, a decades in development and representing the cutting edge of astronomical technology, began its journey to a point 1.5 million kilometers from Earth. Unlike its predecessor, the Hubble Space Telescope, which observed primarily invisible light, James Webb was designed to see the universe in infrared wavelengths. This capability would prove crucial for unraveling the mystery of blue stragglers, allowing astronomers to peer through dust and gas to observe stellar interactions in unprecedented detail. As James Webb settled into its orbital position and began its scientific observations, astronomers around the world prepared to turn this revolutionary instrument toward the oldest mysteries in the cosmos. Among their targets were the globular clusters where blue stragglers dwelt, those impossible stars that had defied explanation for 70 years. The telescope's infrared vision would allow it to see through the crowded stellar environments and detect the faint signatures of mass transfer between stars. After decades of speculation and theory, astronomers finally had a tool capable of revealing whether stellar vampires were real or merely an elegant fiction. The stage was set for a revelation that would reshape our understanding of how stars live, age, and die in the universe's most ancient neighborhoods. The story of blue stragglers begins not with advanced space telescopes or sophisticated computer models, but with a single astronomer peering through an eyepiece on a clear night in 1953. Alan Sandage, working at the Mount Wilson Observatory in California, was conducting a survey of globular clusters, those ancient spherical collections of stars that orbit the Milky Way like satellites around a planet. Sandage was engaged in the meticulous work that defines observational astronomy, photographing clusters, measuring the brightness and color of individual stars, and plotting these measurements on diagrams that revealed the life stories of stellar populations. What he found in his data would puzzle astronomers for generations to come. Sandage was creating what astronomers call a color magnitude diagram, a type of graph that has become one of the most powerful tools in stellar astrophysics. On such a diagram, each star appears as a single point, with its position determined by two properties: its brightness, plotted on the vertical axis, and its color, plotted on the horizontal axis. When hundreds or thousands of stars from a single cluster are plotted this way, a distinctive pattern emerges. Most stars arrange themselves along a curving line called the main sequence, where stars spend the majority of their lives steadily fusing hydrogen in their cores. Above the main sequence, other groupings appear: red giants that have exhausted their core hydrogen and swollen to enormous sizes, and various other populations representing different stages of stellar old age. The beauty of a color magnitude diagram lies in its predictive power. Because all stars in a globular cluster formed at essentially the same time from the same material, their positions on the diagram reveal their evolutionary state. The most massive stars, which burn through their fuel quickly, evolve off the main sequence first, leaving a distinct turn-off point that marks the cluster's age. In an ancient globular cluster, this turn-off point occurs at relatively low masses and cool temperatures, indicating that all the massive hot blue stars have long since completed their evolution. The main sequence should extend downward from this turn-off point, populated only by small, cool, orange and red stars that will burn steadily for billions of years more. When Sandage examined his color magnitude diagrams, he noticed something extraordinary. Beyond the main sequence turn-off point, in a region of the diagram that should have been empty, a small population of stars appeared. These stars were brighter and bluer than the turn-off point, as though they were more massive and younger than any star should be in an ancient cluster. And they did not fit the evolutionary pattern. They appeared to have somehow avoided the fate that had befallen their more massive siblings, remaining bright and blue, while those siblings had evolved into red giants or died entirely. These anomalous stars seem to straggle behind the evolutionary curve, hence the name that would eventually stick, blue stragglers. The discovery might have been dismissed as an observational error or a statistical fluke if Sandage had found these strange stars in only one cluster. But as he and other astronomers surveyed additional globular clusters throughout the 1950s and 60s, blue stragglers appeared again and again. Every ancient cluster examined seemed to harbor at least a few of these puzzling objects, and their presence was not an accident or an artifact, but a genuine astronomical phenomenon that demanded explanation. The universe was showing astronomers something fundamental about stellar evolution, something that did not fit into existing theories. The 1960s and 70s saw an explosion of theoretical work attempting to explain blue stragglers. Astronomers proposed numerous scenarios, each more creative than the last. Perhaps blue stragglers were the products of stellar mergers created when two stars in a binary system spiraled together and combined into a single, more massive star. The merged object would indeed appear more massive and bluer than typical cluster stars, and the merger process might somehow reset the stellar clock, giving the combined star a fresh supply of nuclear fuel. And this merger hypothesis had appeal because globular clusters are dynamically active environments where stellar interactions and collisions though rare, do occur over billions of years. Another theory suggested that blue stragglers might be mass transfer systems, binary stars in which one member strips material from its companion. In this scenario, an aging star paired with a less evolved companion could accrete fresh hydrogen from its neighbor, adding fuel to its nuclear furnace and appearing younger than its true age. The process would be gradual and ongoing, with the vampire star steadily sipping material from its victim over millions or billions of years. This hypothesis had the advantage of explaining not only why blue stragglers appeared young, but also why they tended to concentrate in the dense cores of globular clusters, where binary systems would form more readily and interact more frequently with other stars. A third possibility involved stellar collisions in the dense cluster cores. Perhaps blue stragglers formed when two unrelated stars happened to collide at high speed, their outer layers mixing and their cores combining to form a single rejuvenated star. The crowded centers of globular clusters, where stars are separated by mere light weeks rather than light years, would be the natural environment for such violent encounters. Computer simulations suggested that over billions of years, such collisions might occur frequently, enough to account for the observed population of blue stragglers. The collision hypothesis painted a picture of globular clusters as cosmic demolition derbies, where stellar fender benders and head-on crashes were an inevitable consequence of extreme stellar density. Each theory had supporting evidence and problematic predictions. The merger hypothesis explained why blue stragglers appeared more massive than typical cluster stars, but struggled to account for certain observed details of their rotation rates and chemical compositions. The mass transfer scenario elegantly explained the concentration of blue stragglers in cluster cores and predicted they should often appear in binary systems, but observing such systems directly proved extremely difficult. The collision hypothesis made testable predictions about the frequency and distribution of blue stragglers, but some observed properties seemed inconsistent with violent stellar impacts. Throughout the 1980s and 90s, advances in telescope technology allowed astronomers to study blue stragglers in ever greater detail. The Hubble Space Telescope, launched in 1990 and repaired in 1993, revolutionized the field by providing unprecedented sharp images of globular cluster cores. From its perch above Earth's distorting atmosphere, Hubble could resolve individual stars in the dense central regions of clusters where ground-based telescopes saw only a blur of overlapping light. These observations revealed that blue stragglers were indeed concentrated toward cluster centers, with their numbers increasing as stellar density increased. The spatial distribution strongly suggested that stellar interactions played a crucial role in creating these objects. Hubble observations also revealed unexpected diversity among blue stragglers. Some rotated rapidly, spinning at speeds that suggested they had recently experienced a merger or collision that added angular momentum. Others rotated slowly, more consistent with gradual mass transfer in a stable binary system. Some blue stragglers appeared isolated, with no obvious companion star nearby, while others clearly resided in binary or even triple star systems. This variety suggested that multiple formation mechanisms might be at work, with different processes creating blue stragglers under different circumstances. Spectroscopic observations added another layer of complexity. When astronomers analyzed the detailed wavelength patterns in light from blue stragglers, they found evidence of chemical peculiarities. Some blue stragglers showed enhanced abundances of certain elements, is suggesting they had mixed material from deep stellar interiors with their surface layers during a merger or collision. Others displayed chemical patterns more consistent with gradual accretion of relatively unprocessed material from a companion star. Still others showed signs of having experienced both processes at different times. The chemical evidence painted a picture of blue stragglers as a diverse population with varied and sometimes complicated histories. One particularly intriguing discovery came from observations of blue stragglers in binary systems. Astronomers identified several cases where a blue straggler orbited another star in a close binary pair. In some of these systems, careful measurements revealed that mass was actively flowing from the companion to the blue straggler, with streams of hot gas spiraling inward and adding to the blue straggler's mass. These observations provided the first direct evidence for the vampire hypothesis, showing that at least some blue stragglers were indeed feeding on their companions. However, the observations also raised new questions. How long did the feeding process last? How much mass could a blue straggler steal before its companion was consumed entirely? What happened to the vampire star after its victim was drained? The dawn of the 21st century brought new theoretical insights from computer simulations. As computational power increased, astronomers could model the complex interactions between stars in globular clusters with increasing realism. These simulations suggested that the true picture was more complicated than any single formation mechanism. Some blue stragglers likely formed through direct collisions, others through mergers of binary companions, and still others through mass transfer that might eventually lead to a merger. The simulations also revealed that a single blue straggler might experience multiple rejuvenating events over its lifetime, first gaining mass through transfer from one companion, later colliding with another star, and perhaps later still merging with a third object. Radio observations provided yet another window into the blue straggler phenomenon. Some blue stragglers emitted faint radio waves, suggesting they possessed strong magnetic fields or active chromospheres, regions of hot gas above their visible surfaces. And these radio emissions indicated that blue stragglers were not simply scaled-up versions of normal main-sequence stars, but had unique properties resulting from their unusual formation and evolution. The radio data hinted at ongoing activity, perhaps related to continued mass transfer or the aftermath of recent mergers. As the second decade of the 21st century progressed, astronomers had assembled a comprehensive observational picture of blue stragglers. They knew these objects existed in virtually all globular clusters and many open clusters. They knew blue stragglers concentrated in cluster cores where stellar densities were highest. They knew some resided in binary systems, while others appeared isolated. They knew their chemical compositions revealed long lives despite youthful appearances, and they knew multiple formation mechanisms likely contributed to the population. Yet for all this knowledge, a crucial piece of direct evidence remained elusive: catching a blue straggler in the act of feeding. The problem was technical. To observe mass transfer directly, astronomers needed to detect the faint glow of hot gas flowing between stars, distinguish it from the much brighter light of the stars themselves, and resolve the tiny angular separations between binary components in clusters thousands of light-years distant. Ground-based telescopes struggled with Earth's atmospheric turbulence. Hubble, though excellent for visible light observations, lacked the infrared sensitivity needed to peer through gas and dust surrounding active mass transfer systems. What astronomers needed was a telescope that combined high angular resolution with sensitive infrared detectors, capable of seeing through obscuring material to the stellar surfaces beneath. By the early 2020s, such an instrument was finally in operation. The James Webb Space Telescope, with its 6.5-meter mirror and suite of infrared instruments, could observe the universe with unprecedented clarity at wavelengths invisible to human eyes. Unlike visible light, which scatters and absorbs easily in dusty environments, infrared radiation passes relatively unimpeded through gas and dust. This property made James Webb ideal for studying the crowded, dusty cores of globular clusters where blue stragglers dwelt. The telescope could resolve individual stars in dense cluster centers and detect the faint infrared signatures of hot gas and dust that would indicate active mass transfer. Astronomers wasted no time in directing James Webb towards some of the most intriguing blue straggler candidates identified in previous surveys. They selected targets carefully, focusing on systems where indirect evidence suggested mass transfer might be ongoing. They chose globular clusters at various distances and with different properties, hoping to capture a representative sample of blue straggler behavior. They prepared their instruments to record data across multiple infrared wavelengths, knowing that different temperatures and processes would reveal themselves at different parts of the spectrum. They calibrated their detectors to unprecedented precision, but knowing that the signals they sought would be faint and easily lost in noise. The observations required patience. Unlike amateur astronomy, where one might observe an object for a few hours on a single night, professional observational campaigns often span years and involve hundreds of hours of telescope time. James Webb had to be scheduled months in advance, with proposals competing for limited observing time. Once observations were approved and executed, the data had to be carefully processed, calibrated, and analyzed. Astronomers had to account for instrumental effects, separate signals from noise, and ensure that what they were seeing was real and not an artifact of the observing process. The work was painstaking, but the potential reward was worth the effort. Direct confirmation of stellar vampirism, to the feeding process that kept blue stragglers forever young. The announcement came on January 31st, 2026, in the form of a scientific paper published simultaneously with a press conference that would capture the attention of astronomers worldwide. The research team, led by investigators who had spent years analyzing data from the James Webb Space Telescope, revealed findings that finally solved the 7-decade mystery of blue stragglers. The telescope had observed multiple globular clusters in exquisite infrared detail, and the images told a story of cosmic vampirism playing out across the galaxy. For the first time, astronomers could see the feeding process in action, watching as youthful-appearing stars siphoned gas from their companions in a slow dance of stellar cannibalism. When the path to this discovery had been neither quick nor straightforward. When James Webb began its scientific operations in the summer of 2022, astronomers had submitted proposals for observing time that reflected decades of accumulated questions about stellar evolution. Among these proposals were several targeting globular clusters, those ancient stellar cities where blue stragglers had first been discovered. The research teams wanted to use the telescope's infrared capabilities to peer into the dense cluster cores, regions so crowded with stars that conventional telescopes could not distinguish individual objects. They hoped to catch blue stragglers in compromising positions, locked in gravitational embraces with companion stars and actively stealing their substance. And the James Webb Space Telescope brought unprecedented capabilities to this investigation. Its primary mirror, composed of 18 hexagonal segments coated in gold, collected infrared light across a surface area more than 6 times larger than Hubble's mirror. This collecting area meant James Webb could detect much fainter objects and observe in far greater detail. More importantly, the telescope operated entirely in infrared wavelengths, from near-infrared barely beyond what human eyes can perceive, to mid-infrared, where room temperature objects glow. This infrared vision allowed James Webb to see through the dust and gas that often surrounds interacting stars, revealing structures and processes that remained hidden from optical telescopes. The telescope's location proved equally crucial. Rather than orbiting Earth like Hubble, a James Webb resided at the second Lagrange point, a gravitationally stable location 1.5 million kilometers from Earth in the direction opposite the Sun. At this remote outpost, the telescope could maintain a constant orientation with its sunshield protecting its delicate instruments from the heat of the Sun, Earth, and Moon simultaneously. The instruments operated at temperatures just dozens of degrees above absolute zero, minimizing the infrared glow from the telescope itself that might otherwise overwhelm the faint signals from distant stars. This combination of large mirror, sensitive detectors, infrared wavelength coverage, and ultra-cold operating temperature made James Webb the perfect instrument for studying blue stragglers. The observations themselves required meticulous planning. Globular clusters are not conveniently located in the sky, but scattered around the Milky Way in a roughly spherical distribution. Some clusters appear in the northern hemisphere, others in the southern, and observing them required careful scheduling to ensure they were visible from James Webb's vantage point. The research teams had to coordinate their observations with hundreds of other approved programs, all competing for telescope time. They had to specify precisely which infrared filters and instruments they would use, which stars they would target, and how long they would observe each target. Every second of telescope time was precious, and careful planning was essential to maximize scientific return. When the data finally arrived, transmitted across 1.5 million kilometers of space to receiving stations on Earth, it exceeded all expectations. The images revealed globular cluster cores with crystalline clarity, each star resolved as an individual point of light, rather than blurred together into a confused mass. The infrared filters separated different wavelengths of light, allowing astronomers to construct color images that revealed temperature variations and chemical compositions. More importantly, the images showed extended structures around certain stars, faint glows and wisps that indicated the presence of gas and dust. These structures were the smoking gun, the direct evidence of mass transfer that astronomers had sought for decades. The research team focused their analysis on several dozen blue straggler candidates across multiple clusters. They examined each system carefully, measuring the brightness and color of the stars, searching for companion objects, and looking for any signs of extended emission that might indicate ongoing mass transfer. In system after system, the pattern repeated. The blue stragglers were not solitary stars, but members of binary pairs, orbiting in close proximity to companion stars. And in many cases, the James Webb images revealed unmistakable evidence of material flowing from the companion to the blue straggler. The most dramatic cases showed what astronomers call accretion disks, flattened structures of hot gas spiraling around the blue straggler like water circling a drain. These disks formed because material stripped from the companion star carried angular momentum, preventing it from falling directly onto the blue straggler. Instead, the gas settled into an orbiting disk, gradually spiraling inward as friction between gas particles dissipated orbital energy as heat. The inner portions of these disks glowed intensely in infrared wavelengths, heated to thousands of degrees by friction and by radiation from the blue straggler itself. James Webb's infrared detectors captured this glow in stunning detail, revealing the structure and temperature distribution of the accretion disks. Other systems showed more subtle signs of mass transfer. In these cases, streams of gas connected the companion star to the blue straggler, flowing along curved trajectories determined by the gravitational fields and orbital motion of the two stars. These streams were cooler and fainter than accretion disks, but still detectable in James Webb's sensitive infrared observations. The streams revealed that mass transfer was an ongoing process, not a brief event, but a sustained feeding that could continue for millions or even billions of years. The companion stars were being slowly consumed, their outer layers stripped away atom by atom to feed the insatiable hunger of their blue straggler partners. The data also revealed unexpected complexity in the feeding process. Some blue stragglers appeared to be feeding gently, with material flowing steadily from companion to vampire in a stable configuration that could persist essentially indefinitely. Others showed signs of more violent activity, with irregular variations in brightness suggesting episodic mass transfer events where large amounts of material suddenly fell onto the blue straggler. Still others displayed evidence of past feeding that had ceased, perhaps because the companion had been entirely consumed or because the orbital configuration had changed, cutting off the flow of material. The diversity of behaviors suggested that stellar vampirism came in many forms, each determined by the specific properties and orbital configurations of the binary system. Chemical analysis of the observed systems provided additional insights. By examining the infrared spectra, the detailed patterns of absorption and emission at specific wavelengths, astronomers could determine the composition of both the blue stragglers and their companions. The results confirmed theoretical predictions. The blue stragglers showed chemical signatures of old age, with enhanced abundances of helium and heavier elements produced through billions of years of nuclear fusion. But mixed with these ancient signatures were fresher abundances, patterns consistent with accreted material that had spent less time cooking in stellar interiors. The companions, meanwhile, showed signs of depletion, as though their outer layers had been partially stripped away. The chemical evidence painted a clear picture of material transfer from companion to blue straggler. Perhaps most intriguingly, the observations revealed that the feeding process affected not just the blue straggler but the entire binary system. The companions themselves appeared altered by the interaction, showing distorted shapes as tidal forces from the blue straggler pulled their outer layers into elongated configurations. Some companions appeared overlarge for their masses, puffed up by the same tidal heating that facilitated mass transfer. And others showed signs of rapid rotation, spun up by the angular momentum exchange that occurred during mass transfer. The vampire-victim relationship was not one-sided, but a complex gravitational dance that transformed both partners. The research team also identified several systems in different stages of the feeding process, allowing them to construct a tentative timeline of blue straggler evolution. The youngest systems showed minimal mass transfer, with the blue straggler only slightly more massive than it would have been at birth, and the companion still relatively intact. Middle-aged systems displayed active feeding with prominent accretion disks and streams, and blue stragglers that had gained substantial mass. The oldest systems showed the aftermath of feeding, with blue stragglers significantly more massive than their original birth mass, and companions reduced to small, dense remnants, perhaps white dwarfs or the cores of stripped stars. This evolutionary sequence suggested that blue stragglers could remain active feeders for billions of years, gradually draining their companions until nothing remained to consume. The announcement of these findings sent waves of excitement through the astronomical community. Blue stragglers had been known for 70 years, studied intensively for decades, yet their true nature had remained stubbornly mysterious. Now, thanks to James Webb's infrared vision, the mystery was solved. Blue stragglers were stellar vampires, maintaining their youth through cosmic cannibalism, siphoning fresh hydrogen from neighboring stars to fuel nuclear fusion that should have ceased billions of years ago. The discovery vindicated decades of theoretical work, while simultaneously opening new questions about the prevalence and importance of stellar interactions in shaping galactic evolution. News media around the world seized on the vampire metaphor, with headlines proclaiming the discovery of cosmic bloodsuckers hiding in our galaxy. The comparison, while scientifically imprecise, captured something essential about the phenomenon. Just as legendary vampires sustained their immortality by drinking the life essence of victims, blue stragglers maintained their youthful appearance by consuming the substance of companion stars. The victims, slowly drained of their mass and energy, withered while the vampires thrived in their stolen vitality, allowing them to shine bright and blue in neighborhoods where all their contemporaries had long since faded. The discovery also highlighted the power of infrared astronomy. For decades, astronomers had suspected that mass transfer created blue stragglers, but without the ability to see through obscuring gas and dust to the stellar surfaces beneath, they could not confirm their suspicions. James Webb's infrared capabilities finally provided that crucial observational window, allowing scientists to peer past the veils that had hidden the feeding process from earlier generations of telescopes. The success demonstrated the value of building instruments that observe outside the narrow band of visible light accessible to human eyes, revealing processes and structures invisible to optical astronomy. As word of the discovery spread, astronomers began to consider the broader implications. If blue stragglers formed through mass transfer in binary systems, and if this process was common throughout globular clusters and beyond, then stellar interactions might play a far larger role in galactic evolution than previously recognized. The universe might be full of stellar vampires, hidden in plain sight, their presence affecting everything from the colors of galaxies to the chemical evolution of stellar populations. The discovery of how blue stragglers maintained their youth was not just the solution to a single puzzle, but potentially the opening of a new chapter in our understanding of how stars live, interact, and shape the cosmos around them. To understand how stellar vampires feed on their companions requires delving into the intricate gravitational choreography that governs binary star systems. Two stars orbiting their common center of mass are not simply separate objects moving through space, but gravitationally bound partners whose fates become inextricably intertwined. The closer these stars orbit to one another, the more profoundly they affect each other's structure and evolution. In the tightest binary systems, where stellar surfaces nearly touch across the gulf of space separating them, the gravitational influence becomes so extreme that material can flow from one star to the other, transforming both objects in the process. Every star exists in a delicate balance between two opposing forces. Gravity, arising from the star's mass, attempts to crush all material toward the center, compressing the star into the smallest possible volume. Pressure from hot gas in the stellar interior pushes outward, resisting gravitational collapse. In an isolated star, these forces reach equilibrium, and the star maintains a stable size and shape determined by its mass and age. But in a close binary system, the gravitational pull of the companion star distorts this equilibrium. Material on the near side of each star feels stronger gravitational attraction toward the companion than material on the far side, creating tidal forces that stretch the stars into slightly elongated shapes. Around each star, in a binary system, exists an invisible boundary called the Roche lobe, a three-dimensional surface marking the limit of that star's gravitational domain. Inside the Roche lobe, material is gravitationally bound to the star and cannot escape without additional energy. Outside the Roche lobe, the companion star's gravity dominates, and material will fall toward the companion rather than remaining with its original host. The Roche lobe is not spherical, but rather teardrop-shaped, pointing toward the companion star. The size of each Roche lobe depends on the masses of the two stars and their orbital separation, with more massive stars and wider orbits producing larger Roche lobes. In most binary systems, both stars comfortably fit within their respective Roche lobes, and the stars evolve largely independently despite their gravitational partnership. But as stars age and evolve, they sometimes expand dramatically. Low-mass stars, having exhausted the hydrogen in their cores, transition to burning hydrogen in a shell surrounding an inert helium core. This shell burning causes the star's outer layers to expand enormously, transforming the star into a red giant hundreds of times larger than its original size. If this expansion occurs in a close binary system, the swelling star may grow until its outer layers reach and overflow the Roche lobe boundary. When a star fills its Roche lobe, a remarkable transformation begins. Material in the star's outer atmosphere, now beyond the gravitational point of no return, begins to flow toward the companion star. Gas streams through the narrow channel where the two Roche lobes touch, following trajectories shaped by gravity and orbital motion. This mass transfer fundamentally alters both stars. The donor star, losing material from its outer layers, may halt or even reverse its expansion. The accretor star, gaining fresh hydrogen fuel, becomes more massive and luminous. The mass transfer can continue for millions or billions of years, gradually reshaping the binary system. The fate of the transferred material depends on the orbital configuration and the properties of the accretor star. In some cases, particularly when orbital angular momentum is low, material falls almost directly from donor to accretor, raining down onto the stellar surface in a chaotic process. More commonly, the material carries substantial angular momentum from its original orbit around the donor star. Conservation of angular momentum prevents this material from falling directly onto the accretor. Instead, it goes into orbit around the accretor, forming an accretion disk, a flattened structure of gas spiraling gradually inward. Accretion disks are among the most fascinating structures in astrophysics, appearing around objects ranging from newborn stars to supermassive black holes. In the context of blue stragglers, accretion disks form when material flowing from a companion star cannot fall directly onto the blue straggler, but instead settles into orbit. The disk consists of gas moving on circular or nearly circular paths, with inner regions orbiting faster than outer regions according to the laws of orbital mechanics. Adjacent rings of material moving at different speeds rub against each other, generating friction that heats the gas and simultaneously transports angular momentum outward through the disk. This friction serves a crucial function. As angular momentum moves outward through the disk, a material in the inner disk loses angular momentum and spirals inward toward the central star. The process is gradual, with material taking thousands or millions of years to spiral from the outer disk to the stellar surface, but it is inexorable. The friction also converts orbital energy into heat, raising the disk's temperature. The inner regions of the disk, where orbital velocities are highest and friction is most intense, can reach temperatures of tens of thousands of degrees, hot enough to glow brilliantly in ultraviolet and visible wavelengths. The outer disk, cooler and more extended, emits primarily in infrared wavelengths, making it perfect for observation by James Webb. The James Webb observations revealed accretion disks around numerous blue stragglers, confirming that mass transfer was indeed active in these systems. The infrared images showed the characteristic signature of hot gas in orbital motion, with emission concentrated in flattened structures surrounding the central stars. By analyzing the infrared spectrum, astronomers could determine the temperature distribution across the disks, finding that inner regions were indeed hotter than outer regions, as theoretical models predicted. The disk temperatures, typically ranging from a few hundred to several thousand degrees depending on distance from the central star, indicated substantial energy dissipation through friction, powering the glow that James Webb detected. The mass transfer rates varied considerably among observed systems. Some blue stragglers were accreting material slowly, gaining only a tiny fraction of a solar mass per million years. At this leisurely pace, the feeding process could continue for billions of years without completely consuming the donor star. Other systems showed much higher transfer rates, with blue stragglers gaining substantial mass on timescales of millions rather than billions of years. These rapid feeders displayed brighter, more extensive accretion disks and showed greater variability in brightness, suggesting episodic or unstable mass transfer. The diversity of transfer rates indicated that stellar vampirism came in different intensities, from gentle sipping to voracious consumption. The observations also revealed what happens to donor stars as they are drained by their vampire companions. In many systems, the donor appeared underluminous for its mass, as though partially deflated by the loss of its outer layers. Some donors showed distorted shapes, pulled into teardrops by the tidal forces of their companions, with one side bulging toward the blue straggler in response to gravitational attraction. The most extreme cases showed donors stripped down to their cores, with much of their original hydrogen envelope transferred to the blue straggler. These stripped stars appeared unusually hot and dense for their remaining mass, representing an evolutionary pathway rarely seen among isolated stars. The chemical consequences of mass transfer proved equally revealing. Stars are not chemically homogeneous throughout their interiors, but rather show gradients in composition, with heavier elements concentrated toward the core where nuclear fusion produces them. When a star swells into a red giant and fills its Roche lobe, the material that overflows comes from the stellar envelope, to the outer layers that have undergone less nuclear processing than the core. This relatively pristine hydrogen-rich material, transferred to the blue straggler, adds fuel while diluting the chemical signatures of the blue straggler's own nuclear fusion. The result is a star with a complex chemical history written in its atmospheric composition. James Webb's spectroscopic observations detected these chemical fingerprints with unprecedented precision. The blue stragglers showed elevated abundances of helium and carbon relative to hydrogen, signatures of nuclear burning in their own cores over billions of years. But they also showed abundances of lighter elements consistent with fresher material that had spent less time in stellar interiors. Some blue stragglers displayed unusual abundance patterns that could only be explained if they had accreted material from companions that had themselves undergone nuclear processing, perhaps having already ascended the red giant branch before mass transfer began. The chemical data provided a forensic record of the feeding history, allowing astronomers to reconstruct how much material had been transferred and from what kind of donor star. The timescales of stellar vampirism proved surprisingly varied. In systems where the donor was only slightly more massive than the blue straggler, mass transfer could begin early and continue for billions of years in a stable configuration. The donor would slowly transfer its envelope, while the blue straggler grew gradually more massive, on the process so gentle and prolonged that both stars remained in a stable equilibrium throughout. These systems represented the most sustainable form of vampirism, where the victim was consumed so slowly that it might survive, albeit in altered form, for much of the galaxy's lifetime. Other systems showed evidence of more dramatic evolution. In cases where the donor was initially much more massive than its companion, the onset of mass transfer could be rapid and unstable. As material flowed from the more massive donor to the less massive accretor, the mass ratio of the system changed, altering the size and shape of the roach lobes. This feedback could accelerate mass transfer in a runaway process, with increasingly rapid material flow threatening to destabilize the entire system. Some such systems might end in a catastrophic merger, with the two stars spiraling together and combining into a single, rapidly rotating blue straggler. Others might eject the donor entirely, flinging it out of the system through gravitational interactions and leaving the blue straggler apparently isolated. The James Webb observations captured systems at all stages of this evolutionary sequence. Young feeding systems showed donors still relatively intact, with modest accretion disks and stable mass transfer. Middle-aged systems displayed active vampirism in full swing, with substantial disks, high mass transfer rates, and donors showing clear signs of deflation. Elderly systems showed the aftermath of feeding, with blue stragglers having gained significant mass, and donors reduced to small remnants or perhaps consumed entirely. This observational sequence, combined with theoretical modeling, allowed astronomers to construct a comprehensive picture of blue straggler evolution from birth to maturity. One particularly intriguing discovery concerned the rotation rates of blue stragglers. As material from the donor star spirals inward through an accretion disk, it carries angular momentum that is ultimately deposited onto the blue straggler's surface. This should spin up the blue straggler, causing it to rotate faster and faster as accretion continues. Some observed blue stragglers indeed showed rapid rotation, spinning at velocities approaching the breakup limit, where centrifugal forces nearly overcome gravity. But surprisingly, other blue stragglers rotated slowly, as though they had not accreted significant angular momentum. This dichotomy suggested different accretion mechanisms or perhaps loss of angular momentum through stellar winds or magnetic braking. The observations also revealed unexpected interactions between mass transfer and stellar magnetic fields. Some blue stragglers showed evidence of strong magnetic activity, with flares and variable emissions suggesting active stellar chromospheres and coronae. These magnetic fields, powered by the rapid rotation and deep convection zones induced by mass accretion, could channel inflowing material toward the magnetic poles, creating hot spots visible as variations in brightness as the star rotates. The magnetic fields might also drive stellar winds that carry away angular momentum, preventing the star from spinning up to break-up velocity despite ongoing accretion. The interplay between accretion, rotation, and magnetism added yet another layer of complexity to the stellar vampirism phenomenon. As astronomers pieced together the observational evidence, a coherent picture emerged. Blue stragglers maintained their youth through a sustained process of cosmic cannibalism, accreting fresh hydrogen from binary companions and using this stolen fuel to power nuclear fusion that should have ceased billions of years ago. The feeding occurred through Roche lobe overflow in close binary systems, with material flowing through accretion disks that dissipated orbital energy as heat and gradually delivered stolen substance to the vampire star. The process could continue for billions of years, transforming both vampire and victim, creating stars that defied simple evolutionary classification. The universe, it seemed, it was full of stellar predators hiding among their prey. The discovery that blue stragglers maintain their youth through stellar vampirism carries profound implications that extend far beyond the solution of a single astronomical puzzle. These implications ripple outward through multiple layers of astrophysical understanding, forcing astronomers to reconsider fundamental assumptions about stellar populations, galaxy evolution, and the cosmic history written in starlight. What began as a curiosity, a handful of anomalous stars in ancient clusters, has revealed itself as a window into processes that shape the appearance and evolution of stellar systems throughout the universe. Consider first the immediate implications for our understanding of globular clusters themselves. For decades, astronomers treated these clusters as simple stellar populations, collections of stars all born at the same time from the same material and evolving in isolation according to their individual masses. This simplified picture made globular clusters invaluable as cosmic laboratories where stellar evolution could be studied in its purest form, uncontaminated by the complexities of ongoing star formation or chemical evolution. The color magnitude diagrams of globular clusters were thought to reveal stellar evolution with textbook clarity, each star marching along a predictable evolutionary track determined solely by its birth mass and the cluster's age. The revelation that blue stragglers form through mass transfer between binary stars demolishes this simple picture. Globular clusters are not populations of non-interacting stars, but dynamic environments where stellar encounters and binary interactions fundamentally alter stellar evolution. A star's fate depends not just on its birth mass, but on whether it has a binary companion, how close that companion orbits, and what interactions the binary system experiences with other stars in the crowded cluster core. The evolutionary tracks that astronomers carefully calculated for isolated stars represent only one possible pathway, and perhaps not even the most common one in dense stellar environments. This realization forces a recalibration of how astronomers determine the ages of globular clusters. The traditional method relies on identifying the main sequence turn-off point and the location in a color magnitude diagram where stars are just beginning to exhaust their core hydrogen and evolve off the main sequence. By comparing the observed turn-off point to theoretical models, astronomers can determine when the cluster formed. But if blue stragglers can rejuvenate themselves through mass transfer, appearing younger than they truly are, might other populations also be affected by stellar interactions? Could some apparently young stars near the turn-off point actually be products of binary evolution rather than unevolved cluster members? The presence of stellar vampires injects uncertainty into age determinations that astronomers once considered reliable. The implications extend to larger scales as well. Globular clusters are not isolated systems, but components of galaxies, and their properties influence our understanding of galactic structure and evolution. Astronomers use globular cluster populations to trace the formation histories of galaxies, with cluster ages, abundances, and spatial distributions providing clues about when and how their host galaxies assembled. If stellar interactions can significantly alter the appearance of cluster populations, creating artificially young-looking stars through mass transfer and mergers, then interpreting the light from distant cluster systems becomes more complicated. Galaxies might appear younger or have different star formation histories than surface observations suggest. The discovery also has implications for understanding the integrated light of distant galaxies. When astronomers observe galaxies too far away to resolve individual stars, they see only the combined light of billions of stars blended together. This integrated light carries information about the stellar population, with the galaxy's color and spectrum revealing the average age and chemical composition of its stars. Blue stragglers, by appearing younger and bluer than they truly are, make their host populations appear younger overall. In a globular cluster with a substantial blue straggler population, the integrated light might suggest a younger age than the true formation time. Scale this effect up to entire galaxies, and it becomes clear that stellar vampirism could bias our interpretations of galaxy colors and ages. This bias may help resolve certain puzzles in extragalactic astronomy. Astronomers have long noticed that some elliptical galaxies appear to contain stellar populations too young for the galaxy's presumed age and formation history. These galaxies show blue colors or spectral features suggesting the presence of young stars, yet they show no signs of recent star formation that would explain where these young stars came from. The anomaly has led to various explanations involving late-stage star formation bursts or unusual stellar evolution. But perhaps at least some of these apparently young populations consist not of genuinely young stars, but of blue stragglers, stellar vampires that have rejuvenated themselves through mass transfer and now masquerade as a younger generation. The chemical implications of stellar vampirism also deserve consideration. Stars do not merely shine, but serve as cosmic forges, converting hydrogen and helium into heavier elements through nuclear fusion. When stars die, they return this processed material to the interstellar medium through stellar winds and supernova explosions, enriching the galaxy with metals that will be incorporated into later generations of stars. This chemical evolution shapes the composition of galaxies over cosmic time. But blue stragglers complicate this picture because they lock material away from the chemical evolution cycle, storing freshly accreted hydrogen in long-lived stars that may burn for billions of years beyond their normal lifetimes. Consider the fate of a red giant in a binary system with a smaller companion. Under normal circumstances, this red giant would eventually shed its envelope through stellar winds or a planetary nebula, returning most of its mass to the interstellar medium. The exposed core would cool as a white dwarf, and the ejected material would enrich the galaxy with elements produced through nuclear fusion. But if the red giant has a companion star close enough to accrete material, much of the envelope never returns to the interstellar medium. Instead, it transfers to the companion, which becomes a blue straggler and retains this material for billions of years more. The chemical enrichment that would have occurred is delayed or prevented entirely, altering the chemical evolution of the cluster or galaxy. The prevalence of stellar vampirism remains an open question with significant implications. The James Webb observations confirmed that mass transfer creates blue stragglers, but how common is this process? Are most stars in dense clusters affected by binary interactions at some point in their lives, or is stellar vampirism a rare phenomenon affecting only a small fraction of the population? The answer matters because it determines how significantly we must revise our understanding of stellar populations. If only a few % of stars become blue stragglers, the effect on integrated properties is modest. But if tens of % of stars experience mass transfer or mergers, the implications are profound. Evidence suggests that stellar interactions may be more common than once thought. Surveys of globular clusters find that blue stragglers make up several % of the stellar population in most clusters, and substantially higher fractions in the densest cluster cores. Given that blue stragglers eventually exhaust even their stolen fuel and fade from visibility, the current population represents only the tip of the iceberg, the vampires currently active, while many more have already finished feeding and evolved away. When astronomers account for this observational bias and model the full history of stellar interactions over a cluster's lifetime, they conclude that a substantial fraction of all cluster stars may have experienced mass transfer or merger events. The dynamical implications also warrant attention. Mass transfer between binary stars does not occur in isolation, but affects the orbital motion of the binary system. As material flows from donor to accretor, angular momentum and energy are exchanged, altering the orbital period and separation. In some cases, mass transfer causes the orbit to shrink, bringing the stars closer together and potentially leading to a merger. In other cases, mass loss from the system can cause the orbit to widen. These orbital changes affect how the binary system interacts with other stars in the cluster, influencing the overall dynamical evolution of the cluster. Moreover, binary systems in dense cluster cores can exchange partners through gravitational interactions with passing stars. A binary might capture a third star, forming a temporary triple system that quickly ejects one member, often replacing the original companion with the interloper. These exchanges can create new binary systems capable of producing blue stragglers, even if the original pairing was not conducive to mass transfer. The complex interplay between binary evolution and cluster dynamics means that stellar vampirism does not simply add a complication to our understanding of clusters, but requires a fundamentally integrated approach that considers stellar evolution and gravitational dynamics together. The discovery also has implications for understanding stellar mergers, which represent the ultimate form of stellar interaction. While some blue stragglers form through gentle mass transfer over billions of years, others likely result from violent collisions or rapid mergers where two stars combine in a brief catastrophic event. The James Webb observations provided evidence for both pathways, with some blue stragglers showing the chemical signatures of prolonged mass transfer and others displaying rapid rotation and other properties consistent with recent mergers. Understanding which formation mechanism dominates and under what conditions remains an active area of research. Stellar mergers are not just interesting in their own right, but serve as possible formation channels for various exotic stellar types. Some peculiar stars with unusual chemical compositions or magnetic properties may be merger products. Certain types of supernovae, stellar explosions that do not fit standard models, might result from merged stars that evolve differently than isolated stars would. Blue stragglers provide a laboratory for studying stellar mergers, allowing astronomers to test theoretical models against observed properties of stars that have undergone this violent transformation. The implications extend even to understanding star formation itself. While blue stragglers form through interactions between existing stars rather than through the collapse of gas clouds, the accretion process shares some features with how young stars gather mass from their natal disks. The accretion disks around blue stragglers, though formed through binary mass transfer rather than gravitational collapse, obey similar physical principles to the protoplanetary disks surrounding newborn stars. Studying blue stragglers thus provides insights into accretion physics applicable to other astrophysical contexts, from planet formation to the growth of supermassive black holes. Perhaps most intriguingly, the discovery of stellar vampirism raises questions about how common such interactions might be on planetary scales. If two stars in a binary system can exchange mass, might planets also experience similar interactions? Could a planet in a close binary system accrete material from stellar winds or outflows, altering its composition and evolution? While planets are far less massive than stars, and thus less able to capture material gravitationally, the possibility of planet-star or planet-planet interactions mediated by mass transfer cannot be entirely dismissed. The study of stellar vampirism thus opens conceptual doors to thinking about mass exchange in all types of gravitationally bound systems. The James Webb observations have not merely solved the mystery of blue stragglers, but have revealed stellar vampirism as a fundamental process shaping stellar populations throughout the universe. What once seemed an anomaly, a handful of stars that refused to follow the rules, now appears as evidence of interactions that affect substantial fractions of all stars in dense environments. The discovery forces astronomers to adopt a more sophisticated view of stellar populations, one that accounts for the complex interplay between stellar evolution, binary dynamics, and environmental density. In solving one puzzle, the telescope has revealed an entire landscape of questions about how stars interact, evolve, and shape the galaxies they inhabit. The revelation of stellar vampirism through the James Webb Space Telescope's observations marks not an ending, but a beginning, the opening of new avenues of investigation that promise to reshape our understanding of stellar evolution for decades to come. With the mystery of blue stragglers now solved, astronomers stand at a threshold, equipped with unprecedented observational capabilities and armed with new questions that could only be formulated once the basic phenomenon was understood. The telescope continues its mission, peering deeper into globular clusters and beyond, searching for stellar vampires throughout our galaxy and uncovering the full scope of how mass transfer shapes stellar populations. The immediate future of stellar vampire research involves systematic surveys of globular clusters across the Milky Way. The galaxy harbors approximately 150 globular clusters, each a unique laboratory with different properties that may affect how stellar interactions proceed. Some clusters are extremely dense, with stars packed so tightly in their cores that stellar encounters occur frequently. Others are more diffuse, with larger separations between stars and correspondingly rarer interactions. Some clusters are metal-rich, composed of stars with relatively high abundances of elements heavier than hydrogen and helium, while others are metal-poor, containing stars whose composition more closely resembles the primordial mixture present shortly after the Big Bang. These differences may influence binary evolution and mass transfer efficiency. Astronomers are now planning comprehensive observing campaigns to survey blue straggler populations across this diverse sample of clusters. By observing clusters with different densities, ages, and chemical compositions, researchers hope to understand how environmental factors affect stellar vampirism. Do denser clusters produce more blue stragglers because stellar encounters are more frequent? Do metal-rich stars transfer mass differently than metal-poor stars because of differences in stellar structure and envelope properties? Does cluster age matter, with older clusters having more time to produce blue stragglers through prolonged mass transfer? These questions can only be answered through systematic comparative studies across many clusters. The James Webb Space Telescope is ideally suited for such surveys, and its infrared sensitivity allows it to penetrate the dust and gas in cluster cores, revealing individual stars even in the most crowded regions. Its spectroscopic capabilities enable detailed chemical analysis of blue stragglers and their companions, reconstructing feeding histories and testing theoretical predictions about mass transfer. Most importantly, the telescope can observe clusters across a wide range of distances, from nearby systems only a few thousand light-years away to distant clusters on the far side of the galaxy, providing a comprehensive view of stellar vampirism throughout the Milky Way. Beyond our own galaxy, the discovery of stellar vampirism opens new questions about how this process operates in different galactic environments. The Milky Way is a relatively quiet spiral galaxy with modest star formation rates and a long history of gradual evolution. But the universe contains many other types of galaxies with very different properties. Some galaxies undergo violent starbursts, forming stars at rates hundreds of times higher than the Milky Way. Others are massive elliptical galaxies where star formation ceased billions of years ago. Still others are dwarf galaxies with very low masses and metal abundances. Does stellar vampirism occur in all these environments, or is it sensitive to galactic properties? The Magellanic Clouds, two small satellite galaxies orbiting the Milky Way, provide particularly interesting test cases. These dwarf galaxies have lower metal abundances than the Milky Way and different star formation histories. They also contain numerous globular clusters, some quite similar to Milky Way clusters, and others with unusual properties. Observations of blue stragglers in Magellanic Cloud clusters could reveal whether stellar vampirism operates differently in metal-poor environments. The proximity of the Magellanic Clouds, only about 160,000 light-years distant, makes them accessible to detailed study with James Webb. Even more ambitiously, Astronomers hope to detect signatures of stellar vampirism in distant galaxies millions or billions of light-years away. While individual stars cannot be resolved at such distances, the integrated light of stellar populations carries information about their composition and age distribution. Blue stragglers, by appearing younger and bluer than they truly are, affect the integrated colors and spectra of their host populations. By carefully modeling how stellar vampirism influences integrated light, astronomers may be able to detect the signature of blue straggler populations in distant galaxies, revealing how common stellar interactions are in the early universe. This prospect is particularly exciting because it connects stellar vampirism to cosmic history. The universe has evolved dramatically over its 13.8 billion year history. In the early universe, shortly after the Big Bang, gas was composed almost entirely of hydrogen and helium, with only trace amounts of heavier elements. Stars that formed in this pristine environment had very different structures than modern stars, and their binary interactions may have proceeded differently. As successive generations of stars produced heavier elements through nuclear fusion and dispersed them through supernovae, the chemical composition of galaxies gradually changed. Understanding how stellar vampirism operated at different cosmic epochs could provide insights into how stellar populations evolved over the universe's history. The discovery also motivates searches for other types of stellar interactions beyond the binary mass transfer that produces blue stragglers. In the densest cluster cores, three-body interactions might lead to the formation of triple or even quadruple star systems, creating complex hierarchical arrangements where mass transfer could occur simultaneously between multiple partners. Some of these systems might produce even more exotic stellar types than blue stragglers, and perhaps stars that have accreted material from multiple donors or that have undergone multiple merger events. The James Webb observations have revealed that the universe of stellar interactions is richer and more complex than previously imagined, and blue stragglers may represent just one manifestation of a broader phenomenon. Theoretical work will play an equally important role in the future of stellar vampire research. While observations reveal what is happening, theory explains why it happens and predicts what should occur under different conditions. Astronomers are developing increasingly sophisticated computer models that simulate the evolution of binary star systems, tracking mass transfer, orbital changes, and chemical mixing with unprecedented detail. These models must account for complex physics, including tidal interactions, magnetic fields, angular momentum transport, and nuclear reactions occurring simultaneously in multiple stellar components. Modern supercomputers enable simulations that follow individual binary systems through billions of years of evolution, revealing the full life cycle of stellar vampires from first contact to final merger or separation. Complementing these detailed binary evolution models are large-scale simulations of entire globular clusters. These simulations follow thousands or millions of individual stars as they orbit within the cluster, interact gravitationally, form and dissolve binary systems, and evolve according to stellar physics. By incorporating realistic models of binary evolution into cluster simulations, astronomers can predict how many blue stragglers should form, where they should be located within the cluster, and how their properties should vary with cluster parameters. Comparing these predictions to James Webb observations provides a powerful test of theoretical understanding and reveals where current models succeed or fail. One particularly intriguing direction for future research involves understanding the ultimate fate of stellar vampires. Blue stragglers appear young and will continue to burn hydrogen for billions of years, but eventually even stolen fuel must run out. What happens when a blue straggler finally exhausts its nuclear reserves? Does it evolve like a normal star of its acquired mass? Or does its unusual formation history lead to exotic outcomes? Some theoretical models suggest that blue stragglers might produce unusual types of stellar remnants, perhaps white dwarfs with peculiar compositions, or even supernovae that differ from those produced by isolated stars. Observing the endpoints of blue straggler evolution would provide crucial tests of these predictions. The discovery of stellar vampirism also has implications for the search for planets in unusual environments. Astronomers have discovered thousands of exoplanets orbiting stars throughout the galaxy, but most of these planets orbit single stars or widely separated binary pairs. What happens to planets in close binary systems where mass transfer occurs? Could a planet survive the violent mass exchange between stellar vampires and their victims, or would it be ejected or destroyed by the changing gravitational environment? Some blue stragglers might harbor planets that have witnessed billions of years of stellar cannibalism, offering unique laboratories for studying planetary survival in extreme environments. Future instrumentation will enhance our ability to study stellar vampires. While James Webb has revolutionized the field, it is not the only tool available. Ground-based telescopes equipped with adaptive optics systems that correct for atmospheric turbulence can achieve resolution comparable to space telescopes for certain observations. Radio telescopes can detect the emission from hot gas in mass transfer systems, providing complementary information to infrared observations. X-ray telescopes can observe the high-energy emission from accretion disks where infalling material reaches extreme temperatures. By combining observations across the electromagnetic spectrum, astronomers can build comprehensive pictures of stellar vampirism in action. Next-generation space telescopes already in planning stages promise even greater capabilities. Concepts for large infrared telescopes with mirrors 10 or 20 meters in diameter would provide resolution and sensitivity far exceeding James Webb, potentially allowing observations of stellar vampirism in galaxies halfway across the universe. Proposals for interferometric arrays of multiple telescopes flying in formation could achieve angular resolution sufficient to directly image accretion disks around blue stragglers, revealing their structure in exquisite detail. These future facilities would transform stellar vampire research from a field focused on our own galaxy to one with a truly cosmological perspective. The discovery also opens opportunities for collaboration between different areas of astronomy. Stellar vampirism connects stellar evolution, binary dynamics, cluster dynamics, chemical evolution, and galactic archaeology. Understanding the phenomenon fully requires expertise spanning these diverse subfields, encouraging astronomers to work across traditional boundaries. Graduate students entering the field now have opportunities to contribute to questions ranging from detailed stellar physics to large-scale galactic evolution, united by the common thread of stellar interactions. The interdisciplinary nature of stellar vampire research makes it an exciting frontier for the next generation of astronomers. Public interest in the discovery has been substantial, with the vampire metaphor capturing imaginations worldwide. This enthusiasm presents opportunities for science communication and education. The story of blue stragglers illustrates how science progresses from initial puzzling observations through decades of theoretical speculation to final confirmation through technological advancement. It demonstrates the power of patience in scientific research, with 70 years elapsing between the discovery of blue stragglers and the definitive explanation of their nature. It showcases international collaboration, with scientists from many countries contributing to observations, theory, and interpretation. These themes resonate with public audiences and help convey the excitement and importance of astronomical research. Educational programs are already incorporating stellar vampirism into curricula at various levels. The phenomenon provides an accessible entry point for teaching stellar evolution, binary star dynamics, and observational astronomy. Students can explore color magnitude diagrams, identify blue stragglers, and consider what processes might produce them. The Discovery Timeline offers lessons about scientific methodology and the interplay between observation and theory. The dramatic language of stellar vampires captures student interest, while the underlying science provides substance for serious study. Educators see opportunities to use this discovery to inspire the next generation of astronomers. As James Webb continues its mission, accumulating thousands of hours of observations across multiple scientific programs, the database of information about stellar vampires grows steadily. Each new observation adds detail to our understanding, revealing subtleties and exceptions that test and refine theoretical models. Unexpected discoveries surely await, as they always do when new observational capabilities reveal previously hidden aspects of nature. Perhaps astronomers will find blue stragglers in unexpected locations, or discover new types of stellar interactions beyond simple binary mass transfer. Perhaps the vampire metaphor will prove incomplete, and stellar cannibalism will reveal additional layers of complexity. What seems certain is that the discovery of stellar vampirism marks a watershed in our understanding of stellar populations. The simple picture of stars evolving in isolation has given way to a richer and more complex view where interactions between stars fundamentally shape their properties and evolution. Blue stragglers, once anomalies that puzzled astronomers, now serve as windows into processes occurring throughout the universe in any environment where stars gather in sufficient density. The James Webb Space Telescope has illuminated these cosmic vampires hiding in our galaxy's oldest neighborhoods, and in doing so has revealed an entirely new dimension to the life stories written in starlight. The future of stellar archaeology lies in understanding not just how individual stars are born, live, and die, but how they interact with one another in the complex stellar ecosystems of clusters and galaxies. Each discovery builds upon previous work, with the solution of one mystery revealing new questions to explore. Astronomers now possess the tools and knowledge to pursue these questions, to map the population of stellar vampires across the galaxy and beyond, and to understand how stellar cannibalism shapes the universe we observe. The hunt for vampire stars has only just begun, and the coming decades promise revelations that will continue to transform our understanding of how stars shape the cosmos they inhabit.